Is that okay? Now people see the screen. You see the screen?
Yes, I can see.
Okay, good.
Okay. Before you start, let me introduce you, in particular to those who are not familiar with you. So I can copy your CV from your personal web page.
It's old. It's old. I don't change my web page. It's fine.
So Yann Mambrini is our old friend, good friend in France. He's in at the moment University of Paris, Saclay, CNS researcher since 2004, and he's also director in the research group. And then I think he's an expert on dark matter models and also phenomenology in spectrometry models and string motivated models. And I think since I started working on dark matter, we started a collaboration. Before we never collaborated, but dark matter make some connection between us. And we will hear today about dark matter, and the title is The Hot Universe to Dark Matter. So I'm looking forward to Yann's nice talk.
Thank you, Yunmin. Thank you. It's always a pleasure to come in Korea, I should say, even if I'm not in Korea. Yeah, there is a very great link between me and Korea. It's always a pleasure to come to Seoul and other cities of Korea, but it's true that since 1 year, things are a little bit more complicated. I hope I will be able to come next year to visit you. I always love your country, you know, very great country, great people. I love Korean people. Anyway, this talk, I'm very honored that you asked me to give a talk in your university, you mean? I will mainly discuss this region of the universe, which is around the reheating time. I don't know the level of specialization of the audience, so I will try to be at the pedagogical at the maximum I can. Normally, I mean, you don't need to have knowledge about dark matter normally to understand the talk. I will try to reintroduce the main concept. It's mixed between results we got recently and work in progress. And the main point I want you to keep in mind after my talk, if I succeed, keeping in mind something, it will be the kind of complexity we have in the very early phase of universe after inflation. This region, which is between the inflation and the reheating, which is a region quite complex because that's why I put a sentence of Boltzmann, because it's a region where the energy is a mixed state between energy coming from the condensate of the inflaton, which is not yet completely destroyed, and the energy of a thermal bath will begin to be produced, but which is sometimes not yet thermalized. So, and even if it's thermalized, but there is no entropy conservation in the thermal bath, of course, because you received energy injected by the inflaton. So the equation, you know, when you work in the classical FIMP or classical WIMP does not work in a sense. The Boltzmann equation, you know, has to be changed, especially because the temperature does not evolve the way it evolved in an adiabatic universe. Of course, the entropy is conserved at the whole, but the entropy in the thermal bath is not conserved. So I will try to give you these kind of hints during this talk. Just for making a little publicity, so that's my textbook. So now I will make publicity and review my talk that will be released on October 7. It's around 500 pages. I'm very honored because Jim Peebles still cannot have gave each one forward of the book. So it's really a textbook for students where I try to gather all the knowledge you need, which is what I call a tool book, which will be a book very useful. It's not a book to, I would say, really understand the concepts. So it's more for graduate students and over. But it's more a book for physicists who need to make a computations and who are not specialists in some field. For instance, all the scattering process are computed. So there's something like 25 scattering process and annihilation process and decay process computed step by step. You have the physics of universe where you have, of course, all of this Compton effect or this kind of stuff computed also for students step by step, and some introduction on inflation also. Oops. Which I try to understand. So it's really a four-particle physicist. That's why I call it particles in the dark universe. Yeah, I try to unify the notations, the energy, and all in GV, etc. On the point of view of a particle physicist, because a lot of books written concerning cosmology or even dark matter are more written by astrophysicists or cosmologists, few by particle physicists, Profumo book, of course, but few particle physicists. So I really try to, which means the concept is amplitude square, and is really from quantum field theory point of view. So, okay, this is what I tried. I hope it will be useful. So I always also introduce a talk by the first dark matter paper when we discuss about dark matter, and I always propose people to read this nice paper, which is from 1906 by Henri Poincaré, which propose the word dark matter, okay, in his first paper. Here you see dark matter, here you see it's his own translation, 1906. The word dark matter, so he translates himself from a French version of his article. In fact, it was a lecture he was given in Sorbonne. So it's translation of matière sombre in French. It translated to dark matter. And that's the first time someone computed the presence of dark matter in a galaxy, especially in the Milky Way in this case, just from the Earth orbit, in fact, and the velocity of the sun around the galactic center and the velocity of the Earth around the sun. Comparing both, we could compute dynamically the mass of the galaxy and compare with the number of stars. In his conclusion, of course, it's a simple computation, but he concluded that there is no dark matter, of course, because it doesn't have the data at this time of Hubble, etc., of Ziki. But it's the first time there was a dynamic computation of a mass of a galaxy using the kinetic theory of gas that Kelvin gave in the lectures. It's lectures Kelvin did in Baltimore in 1904. You can find the lectures of Kelvin where he proposed to use and to see galaxies or stars like a particle and a gas, a system of a gas, and acting, not computing each velocity of galaxy or stars, but using Virial theorem and computing mainly the mass from statistics. Okay, so this is an interesting article if you are interested in. So just remind you what is a WIMP paradigm on the dark matter, because we'll go beyond WIMP. So before going beyond the WIMP, I need to recall you a little bit why we call it a WIMP paradigm or WIMP miracle. So the plot I will show are extracted from our review, The Waning of the WIMP, which is quite a large review on the subject I made with my students and Stefano and Farinaldo. The main constraint we have from the WIMP, I would say, is more direct in a sense, because the dependence on these limits are mainly due to nuclear physics and small dependence on astrophysics, which is not the case for indirect detection, where you have much more constraints on if you look at positrons, for instance, annihilation to positron, you need to know the loss of energy of a positron in the galaxy. If you look at gamma production from annihilation, you need to know some background, etc. Direct detection is more pure, I will say. It depends mainly on there is some uncertainties of around 100, which is quite large, but this 100 uncertainties is coming from maybe nuclear physics and form factors. So dark matter hit a nucleus. I think this I think you can know it. I think, and you measure the energy of recall through ionizations and scintillations, and you combine both. And combining the ionization and scintillations, you can extract the mass of the incoming particle, and I mean a link between the mass of the incoming particle and its interacting cross section on the nucleon. So the uncertainties is coming from the fact that you measure an energy of recall from a nucleus, and you need a coupling to quark, to parton, gluon and quark. And from nucleus to the quark, you need to pass nucleus, nucleon, parton. So you have 3 steps, and on each step you have some uncertainties, nuclear uncertainties in one sense, and of course the nucleon uncertainties, which mean I need the form factor of the nucleus, and I also need the contents of the quarks in the C of a nucleon, for instance. How many strange quarks are present in a proton? This is not well known because you need a lattice QCD, etc., because you don't know how many charm or strange quark are present in the nucleon C. So this kind of uncertainties, if you couple to the Higgs, for instance, where the UKW of the Higgs is larger for the charm, the density of charm in a C of a proton is important if you do the Higgs portal, for instance. So these kind of uncertainties give you a factor 100 more or less on the cross section, but it's doable. So the rates, as I say, for D-ray detection is proportional to the number of targets here, to the number of particles who hits the nucleus, of course, so the local presence of dark matter, to sigma v, okay, and sigma v depend on the velocity, or sigma v depend, differential sigma v, so differential cross-section depend on the coupling of your model, so BSM model, and you need, of course, to know the velocity of dark matter, which is a kind of distribution around the sun. So depending on your model, it can be, this distribution can be important if you look at model, for instance, where you exchange pseudoscalar, where you have velocity dependence on the cross section. So if you have S wave, for instance, this distribution is not so important. I mean, there is some effect, but of the order of 1. But if you have you exchange a pseudoscalar, for instance, you can have velocity dependence here because you introduce a gamma 5 if you want for students, introducing gamma 5, make a cross-section velocity dependence. And in this case, you can be very dependent on the Q of the distribution because you need very large velocity to observe something. And the large velocity is a Q of the distribution, and the Q of the distribution depends on which kind of astrophysical model you have. So usually it's not really dependent, but you see you have a link between the cross-section and the distribution. So in sometimes this distribution is dependent, in other time is not. So except this kind of uncertainties, the limit is quite well known. So this is what I told you, for instance, for a kind of uncertainties, which is important, which is a form factor. This is a kind of Helm form factor I take as an example. It's a form factor, which means what is the dependence of the coupling in a sense, or how many nucleons see a particle with a given wavelength passing through a nucleus. And it's easy to understand the dependence on Q, which means the dependence on the wavelength. Easy to understand that if you have a large wavelength, I will see all the atom, but if I have a short wavelength, I will see just one nucleon. So it's more interesting to look at the form factor for large Q. It's easier than the small Q, QR if you want, which is the exchange momentum. If your exchange momentum is small, you will see much more particle, and it will be proportional to the mass square because the amplitude is proportional to A. So xenon having around 130 nucleon, you have a factor 10 to the 4 more effects, let's say, or number of events for low momentum transfer than from large momentum transfer, which is also the difference between spin dependent and spin independent, because in spin dependent cross section, of course, you have only 1 or 2 particles, which is not paired. So you act only on 1 particle. So this factor S square is quite important because this is the one which increased quite a lot the number of events you expected. So okay, this is just to give you some hints about where the limit is coming from. So this is a typical form factor depending on the xenon or A. So you see that it's for energy below keV, around 0 to 10 keV or 100 keV. This is where you can have a form factor which is quite large. So if you have a small energy of recall, which is in this case here, right? If I go to larger energy of recall, I am in this case here, and I don't see more or less anything. And it's quite nice in a sense because this is the energy you expected in the Milky Way, because the velocity of the Earth around the Milky Way is around, I'd say, 240, 300 kilometers per second, which is 10 to minus 3 C. So if I do 1/2 of mc square, more or less, or 1/2 of mv square, to have the kinetic energy of a dark matter, I have something like 10 to minus 6. So because c square will be, v square will be 10 to minus 6 c square. If I take a velocity of 300 kilometers per second, which is typical velocity in the solar system, so for 1 GeV particle, I expect 1 keV energy of recall. Okay, so kinetic energy of a 1 GeV particle in the solar system is around 1 keV. So the keV is typical energy you expect when you hit this kind of nucleus. So this is wavelength around 1 keV, which is good because 1 keV, as you see, is energy where you hit more or less all the nucleon in the nucleus. By the way, don't forget that it is a detector who hits the dark matter and not the inverse. The sun is turning in a halo which is fixed. So it is the experiment who hits the dark matter and not the inverse. So the experiment is the dark matter at the velocity of the sun around the galactic center, which is around 240 kilometers per second. So all to tell you that the conditions are quite okay and quite good to something. What do we expect? What do we expect for a WIMP? So it's easy to compute also the electroweak cross section you expect from on nucleon. Okay, in this case, on a proton, for instance, usually the direct experiments give a limit for proton with the hypothesis that it's the same for a neutron. Is not always true because you can have, of course, coupling. If you have a Z prime, you can have a coupling which is isospin dependent. But roughly speaking, you can suppose that the interaction of the proton is the same on the neutron. You can even fine tune. You find coupling of neutron to proton to exactly conserve the xenon recall energy. It was a trick which was used 10 years ago when they wanted to make compatible the Dama experiment with the xenon experiments. Dama was sodium, etc., and xenon. So they tried to play with the coupling of proton neutron to cancel the energy of recall, the scattering on the xenon and not on Nr or Ac or silicium. So, but let's suppose that it's the same cross section for nucleon. The cross section is around the Fermi constant square m chi square because we are of course non-relativistic. Okay, so it's classical physics, classical quantum mechanics, much below the electroweak scale. So it's non-relativistic and below the electroweak scale. So gf square m chi square. Chi will always be my dark matter candidate in all my talk. It's a good approximation, and if you put some numbers, it's easy to see that it's around 10 to minus 9. Okay, if I take 1 GeV dark matter, this is around 10 to minus 9 because it's 1 divided by mw square multiplied by g square, so g to the 4. So it's around 10 to minus 9. So you expect a cross section of 10 to minus 9 GeV minus 2 for 1 GeV dark matter. If you prefer in centimeters square, it's 10 to minus 37. So for people who know it by heart, so this is GF square, just that, GF square multiplied by 1 GeV square. So 10 to minus 37 centimeters square, or if you prefer 10 to minus 9 GeV minus 2 is a typical electroweak cross section. So if you have a WIMP, which is a kind of weakly interactive massive particle, you expect a cross section of 10 to minus 37 centimeters square. For the students, they can reduce the computation with a link between a GeV and a centimeter square. So which means 10 to minus 37, if I put a plot with a cross section here in centimeters square and the mass of dark matter here, For 1 GeV dark matter, it should be around here, okay, and for 10 GeV dark matter, it should be around here because it is proportional to m square. So you see that you expect a cross section, a WIM cross section, which means more or less Fermi constant around this region here, much above the limits that I plot here. The last limit of xenon 1 ton, Lux, Panda X, they are always more or less the same. And we have quite a large gap between what you expect from a classical WIMP, I would say, which is heavy neutrino if you want, SU2 charged particle, call it whatever you want, and the limit you have here. Okay, it's around 9 to 10 order of magnitudes excluded. I mean, the heavy neutrino was excluded by Olive and Hall already in 83. So you can imagine in 1983 already the heavy neutrino was excluded, so 30 years ago. So since 30 years, all what happened it is that you are more and more precise in experiments. So if I take classical coupling of G1, G2, G3 from standard model, micro section, if I take macro section, which is less than my electroweak cross section and multiply by 10 to minus 10, because I see that I have around 10 to minus 47 as the limit. This is the future limit of the 1 ton, you reach around 10 to minus 47. So it corresponds, if you want, if I translate this limit as a coupling, as a standard model like coupling, it corresponds to a coupling of 10 to minus 5, more or less. So it's, in this case, we can say that it's not exactly a WIMP barrier. So I don't even take the recarbonance problem. I just put the constraint and ask which kind of coupling I expected. 10 to minus 5 is quite far from the classical. You see, standard model has coupling of the same order of magnitude. It's around 1, okay, of the order 1 for U1, SU2, and SU3. So when you reach 10 to minus 5, the most important conclusion of this is that if you find dark matter, you probably find another sector of the standard model. In this case, in this sense, looking for dark matter is not only looking for a new particle, to my mind, is looking for a new sector of the standard model, which is quite new. 10 years ago, I would have tell you if we find that we were here 10 years ago and at like Dama, something like that, and I would have tell you if we find dark matter, we just find an new electroweak matter, both. Okay, what else? I think now more and more precise is the direct detection experiments. Um, More and more sure it is that we'll reach a new sector of the standard model, which will need or a new gauge group, or a new heavy sector, or a new dynamical sector, for instance, a new heavy Higgs, whatever you want, can be a Yukawa and a Higgs. I talk the G, of course, because I think as a gauge coupling, but it can be a Yukawa if you want. So we reach a new sector, and if it is a Yukawa for the one, it corresponds to heavy mass. So, but why are we so attached to this WIMP-like particle? Of course, because of what we call the WIMP miracle. The WIMP miracle being the fact that if you solve the Boltzmann equation here, you need a cross-section of around, so 10 to minus 26 centimeters cube per second. If you translate it, is around 10 to minus 37 centimeters square for cross-section here, for something which is around the velocity of light. So it's a cross-section which is around 10 to minus 37 centimeters square. So for a weak cross-section, you expect a radical balance of around 0.1 when you solve the Boltzmann equation. This is why we are so attached to it. So if I take this kind of cross-section, I have, in fact, so the same, I put the Fermi constant here to have the cross-section as function of Fermi constant. I see that if I plot my Rayleigh carbonance with time, this is the time here. So this is when the dark matter is in thermal equilibrium. This is now. So the dark matter is kick off the thermal equilibrium. I will go into details, more details in the following slides. And then there will be a time where the expansion will dominate, and for the cross-section, which is around 10 to minus 26 centimeters cube per second, we observe real density which is compatible with Planck. So this is just an illustration of this. This plot is just the density here that I plotted it solving the Boltzmann equation. So I know that if I have a cross-section which is larger than the weak cross-section, I will have not sufficiently dark matter because I will have some annihilation here that will destroy my dark matter. But if my cross-section is too small, I will have an overabundance of dark matter. So this is why we are so attached to it. But that's why you understand quite well that the same diagram giving me this annihilation here I see from the Boltzmann equation, dark matter and some model, the same equation which ensure me, if you want, a thermal equilibrium, is the same diagram that give me the scattering on the proton. So it's exactly the same diagram. So if I want this cross-section to be sufficiently large to annihilate sufficiently dark matter and to avoid overabundance, I automatically have a strong, a large direct detection cross-section. So there is really a direct link. It's exactly the same. M square is the same. Of course, you have some factors if you want, but of unity. But M square is the same in the main of the case. It's not the same if you have a pseudo-scalar exchange or axial vector. But if you have S-wave exchange, it's exactly the same diagram for annihilation and for the same amplitude square for annihilation and for scattering on the proton. So if I want to keep this one large to avoid overabundance, I will have automatically this one large. So I will be excluded by direct detection experiments. In a sense, direct detection experiments tend to push you to low value for M square, so to large Rayleigh balance, okay? Because the smaller is the scattering, the smaller is the annihilation, and the smaller is the annihilation, the larger is the density. So you go to over density. So the more I have constraint on direct detection, the more I am on this line going up, okay? So we are here at 1 ton at the limit. And of course, if we go retreat, more and more you will have overabundance and will be difficult, more and more difficult to find models respecting at the same time scattering limits and annihilation limit from Planck or Boltzmann. So that's a summary of the limits, and that's why we got some problems with the WIMP because Planck, and of course you also have LHC production of dark matter, which give you the same kind of diagram you see. So, and I didn't put indirect detection constraint, but all these constraints are the same thing that for classical WIMP, which is classical particle, which is weakly interacting massive, weakly interacting and massive, you got some constraints which are quite difficult to get rid of. Even if you go beyond the Z, you go to Higgs portal or to a Z prime portal, it's already the same thing. So Z portal, as I told you, is excluded since a long time. So this is the mass of dark matter and the coupling to the Z. To respect the value map, you should stick here, or Planck, if data, you should be on this red line here. And it's already excluded by Lux since a long time. Xenon 1 ton is there, LZ is there. So LZ is the future, is prospect, but I mean, Z portal is excluded by, as I told you, by a coupling of around 10 to the 3. So it's a 6th order of magnitude, at least. This corresponds to the cross-section we saw in the plot before. So you have 6th order of magnitude of the cross-section excluded already. So this little shape here is coming from the fact you are on the Z pole. Okay, this is half the mass of the Z, because half the mass of the Z, you can have smaller coupling because you enter a resonance for the annihilation. So you can allow smaller coupling and having symmetric balance because you have the effect of the pole here. But anyway, even on the resonance, you still are excluded by Lux. Higgs portal is also excluded by Xenon 1 ton already, even when you are on this half of the Higgs of the mass. And if you play with the Z prime here, of course, you have one new parameter. This mass of the Higgs is fixed, the mass of the Z is fixed. But of course, if you play with a Z prime, you have a new parameter, which is the mass of the Z prime. So you have 3 parameters: mass of Z prime, coupling, and mass of the dark matter. In this case, if I plot the mass of Z prime and the mass of chi, and I fix my coupling to be gauge coupling of the order of 1, my constraint go on the mass of Z prime. I need very massive Z prime to avoid deradation constraints. So if I took the LEP and LHC exclusion region and the Lux, which is direct detection exclusion region, what is left is this region here, which means you need a Z prime around 3 to 4 TeV. So BSM scale around 3 to 4 TeV to be not excluded by direct detection nor by LHC or LEP. And Xenon 1 ton will exclude, by the way, this region here after 5 years of data. So if Xenon 1 ton say nothing, it means the particle exchange should be more than around 7 to 8 TeV. So you should be here okay, if you don't see something. So if you don't see nothing, it means the BSM scale corresponds to a exchange particle above around 10 TeV, much above the electroweak scale. So it's always go in the same direction. You will need not only a new particle, but a new region, a new gate group, I forgot what I wanted to say, but you need something new, not a new particle, a new sector, yes, a new sector. So nowadays, you see, you can have, as I told you, or you have, as I told you, so a coupling which is correspond to 10⁻5 to respect the dark matter or the electron, or if you translate it into a massive particle you mediate, it should be more than 2 to 3 TeV with a coupling of 1. So it's a big hint toward the idea that we need a really physics beyond the standard model. What is interesting and why we are so attached by the WIM, the main point is that we are in fact completely independent from the initial condition. And this is something very interesting in the WIM, it is that you don't care about the thermal history of universe. Whatever you do, you know that you begin at a time where you enter thermal equilibrium. So you begin more or less at the temperature at the mass of the dark matter. And what happened before inflation, reheating, preheating, whatever you want, thermalizations, decay of the inflaton, injection of entropy through phase of dominated by a massive particle, biogenesis, whatever you want, gut theory, you don't care. Because once you know dark matter was in thermal equilibrium, you can consider that your universe begin by this, and you can do everything from that without asking any question about the early universe. I think that one of the main reasons why people were also working in WIM, because you don't need to know anything about the complications due to the early universe physics. But of course, as the WIMP is more and more excluded, we need to see alternative ways to obtain the right radiocarbonance. Some people call it FIMP miracle in the sense we could freeze in massive particles. FIMP is very old. The freeze-in exists since at least 83 with the paper of Primack and Pagels for the gravitational dark matter. Gravitational is a FIMP, okay, which is freeze-in or feebly interacting, depending how you call it. So just to remind you in this story, what is a freeze-in compared to the freeze-out. So the classical WIMP is in red here. The classical WIMP, I show you, this is the plot I show you with the sigma V before. So you are in thermal equilibrium and the cross-section decrease, the radical balance decrease until the moment where the expansion dominates and you reach the observed abundance by Planck or the volume map. So this in red is exactly the same plot I showed you before of the radical abundance as function of time. And in blue is the equilibrium abundance, which means the abundance where you enter my equilibrium. Of course, it's per co-moving frame, per co-moving volume in this case. So this is the density of the photon, if you want, okay? And of course, you know the density of dark matter and the photon. There's a factor 9 order of magnitude between the two. You have 10 to minus 9 more or less dark matter than photon. Of course, the universe is dominated by dark matter because it's much more massive than the CMB temperature. So the energy density is dominated by dark matter, but the number density is in universe is of course dominated by the photon. So you have very few dark matter in number density. You have another kind of freeze out, which is, this one I call it the infrared freeze out because it happens quite late in time when the temperature is below the mass of dark matter. But you have also ultraviolet freeze out, which is the case of neutrino. Neutrino freeze out of the bath, so he is kicked off the bath because the coupling, in fact, is quite weak, and it's because of the cross section, which began to be smaller than the Hubble rate that is frozen out. Here, it's because you cannot produce anymore because the bath is not sufficiently energetic to produce dark matter. Then dark matter is frozen from the bath. In the case of neutrino, is another mechanism. It's frozen while being relativistic, so it's completely different. Neutrino is frozen out of the bath because its coupling is very weak, and the cross-section neutrino to electron decrease much faster than the Hubble constant. The Hubble constant decrease, but the scattering of neutrino electron decrease faster because it's t squared than is t to the 5, sorry, and the Hubble constant decreases at t squared. So the cross-section neutrino, electron decreases at t to the 5, so much faster than the Hubble rates. That's why the neutrino freeze out. So it frees out while being still relativistic, because it frees out at 2 MeV, and so a lot of things change on neutrinos. That's why you still have radiative neutrino in the entropy. So they still contribute to the entropy. The freeze-in, you have the same kind of things. You have the infrared freeze-in, which is a small coupling. This time, if you have a small coupling, in fact, you will produce the dark matter very smallly. So it's not at the beginning in thermal bath, and you produce it very slowly, but you produce it out of the bath. Here, you produce it inside the bath. You see the black dot is the dark matter. So dark matter is produced inside the thermal bath and is kicked off the bath. Okay, this is freeze out. Freeze in means you produce dark matter, but still outside of the bath, because never the dark matter enter in the thermal equilibrium of the bath. Okay, and the production rates stop when the Hubble expansion dominates on the production rates. So if you take an infrared freeze in, which is a fixed coupling, lambda square, for instance, just suppose lambda square, Higgs square, and dark matter square, the simplest model you can imagine. If you have a lambda square, so a coupling of around 10 to minus 11, the Hubble constant will dominate the universe. I mean, will dominate the scattering, the production rate before they reach the thermal equilibrium. So it's a very easy computation to do. If you have 10 to minus 11 coupling, you reach the aurelic abundance, the one you want, before reaching the bath. Of course, if I increase my coupling, there will be a moment where I reach the equilibrium here, okay? But I mean, you should reach it before at a temperature above the mass of dark matter. But if you have a small coupling, you will produce it and you will be frozen around. It's interesting if you make the exercise, because it does not depend on the mass of dark matter. The lambda 10 to minus 11, it's an universal value. If you have a coupling of 10 to minus 11, you will produce the right amount of dark matter through freeze in. Okay, this is always the case. And you have the ultraviolet freeze in, which is equivalent to the neutrino if you want, or the gravitino in this case, where you are frozen because your coupling is small. So this, I mean, your coupling, because your coupling is reduced by a mass scale. This, your neutrino is frozen because the Fermi constant at 2 MeV is an energy on mw squared, because you are below the electroweak symmetry breaking energy. So you have a scattering which is in energy to the 5, okay? Here the same for the gravitino, because you are at a scale below the scale of supersymmetry breaking. So you have 1 on M Planck, which appear 1 on F for those who know supersymmetry, 1 on F, F being the breaking scale parameter, which is the product of the mass of the gravitino and M Planck. So you are below F, so below the breaking scale. In this case, you are exactly the same case of the neutrino. It's a point by point a copy. By the way, I remind you that the gravitino was first proposed by Volkov and Akulov, in 76 as a neutrino. Okay, the gravitino was a fermion boson. The gauge fermion of an interaction. Okay, so gravitino is exactly the same physics as a neutrino, and you just replace the scale of electroweak symmetry breaking by the scale of SUSY breaking. So this is called freeze in, which means you produce the particle and it froze before reaching the thermal equilibrium of the standard model. So for that, you understand we need to know the thermal history, because you understand quite well that if you are in thermal equilibrium, okay, and you freeze out, you don't need to know what's happening here. But if I begin from there, it's completely different, because my initial conditions are very important, and all what's happening here depend on what happened in the early time. So when you do freeze in, you need here to know what's happening here and to know the temperature, etc., because the density is not known. When you're in thermal equilibrium, you know the density is one of the photon, and you know the density of the photon, which is given by the classical Boltzmann formula. In this case here, you produce something in a bath which is not thermalized, for instance, you need to know distribution functions, etc., etc., etc. So, as Boltzmann told you, the variable energy, the main object at stake in the struggle for existence and the evolution of the world, which is said like more than 1 century ago, which is exactly true. So I just remind you the story of universe before you are in a thermal equilibrium. So this is why you need to to care when you do WIMP, okay? But when you do FIMP, you need to see what's happening there, okay? So you have a pattern of inflation with a slow roll. I will not go into details for the inflation, but I think you have the minimum knowledge you know about inflation. So here the value of the field inflaton is almost constant, and then you enter the oscillation phase where the density of energy of rho phi acts like a matter field, okay? So it's not a matter field, so be careful. It's really because the equation of states of an oscillating field, so it's a background who oscillates, and you can show easily that the oscillation, I mean, it's not exactly true, by the way, but if you take a quadratic potential, the evolution of a background field, like an action, for instance, that's why action is a dark matter, even if it is electron volt, because it's a cold dark matter. A background field which oscillates with a quadratic potential is a matter field, even if it is very, very light, much less, the mass much smaller than its energy stored in the condensate. An oscillating field has an equation of state of a matter field for quadratic potential and of a radiation field for a quartic potential, but I will talk a little bit about it later. But this oscillation phase, in fact, behaves, the inflaton here behaves like a matter field, okay? So that's why it's a matter domination. So we have an inflation dark energy domination, then inflaton decays. He dominated the universe during the time of decay, and when he completely disappeared, when the amplitude of the oscillation decreased and reached, and so the universe, of course, begin to be heated, you produce more and more photon by the decay. And when the energy density of the photon, in fact, reach the energy density of the inflaton, you begin a radiation domination phase. And in this matter domination phase, you should divide it in two phases, because you have the first part when the photons are not yet sufficiently thermalized, another phase where it is thermalized. So you see the complexity. So you have a radiation domination where, of course, the universe is dominated by thermal photon. You have a phase of matter domination where still the photons are thermal, but the evolution of the scale factor is dominated by the matter. So when you solve the Boltzmann equation, so here the Boltzmann equation is easy, is a thermal distribution in a universe where the scale factor is 1 divided by the temperature, mainly because you have entropy conservation. Here in the bath, you don't have entropy conservation, so you have a region here where you have thermal photon, but you are not conserving entropy because your thermal bath still receive entropy from the decay of the inflaton. So the evolution of the scale factor is much more dependent and different here than here. And here is a little bit even more complex because the photon did not yet thermalize. So you don't have the classical distribution function, no Fermi-Dirac and Bose-Einstein. You have to compute your distribution of photon, which depends this time on the inflaton energy, which has been produced, and so on the mass of the inflaton, okay? Here, the thermal distribution depends only on the temperature. Here, it's non-thermal, so it depends mainly on the characteristic of the inflaton, okay? So this region is different. And of course, here, you have so you can produce dark matter here, you can produce dark matter here, you can produce dark matter here, and you can produce dark matter there, okay? There is a WIMP, and all this region, you can produce dark matter with a different way. So here you produce by gravity, by coupling to the gravity, gravitational production. And here I will discuss how you can produce it here. So I will do a progressive approach from no limit to Newton, if you want, the same way to see you how we can study this region of universe here. I'll show you this region here and point by point, okay? So I will do step by step. So the first vision, which is the easiest one, is to say that you have inflaton will dominate, then radiation will dominate, and at this temperature here, it's a reheating. Okay, this is what you call instantaneous reheating. Why not? You say at this value here, when reheating, well, inflaton, I put one here and don't care about the decay, and I suppose that all the energy stored in the inflaton will go to radiation. You have to be careful with that, of course, because depending when it happens, the density will not be the same because the evolution of the inflaton with the time is a matter evolution, whereas this one is a radiation evolution. It evolves in 1 on 8 to the 4. This one evolves on 1 on 8 to the 3, A being the scale factor. So if it happens before or after, the density will have not be the same for the inflaton. If both is 1 on 8 to the 4, you don't care. But if one doesn't evolve like the other one, if it is matter and radiation, you should be careful of how it decays, because if it's happening there or there, it changes a lot. So this is what we call non-instantaneous reheating. So this is the first step, going, if you want, from Noleme to Copernic, if you want. So you make a first step where you have to be careful that the inflaton does not decay instantaneous. And so during this time here, you have very energetic particle, of course, because inflaton here has a large energy because it's not diluted yet. So the energy which will be stored in the thermal bath will be very large. So even if you have few particles produced, their energy is very large. And in a lot of cases, this is this particle that will produce the dark matter, because even if there are few, the energy they have in the bath, we can suppose it's thermal now, is very huge, and this is what will produce the most amount of dark matter. So this is important to take into account the non-instantaneous rating. So if I take instantaneous rating is rho phi, then 0, then the temperature decrease as A minus 1. So it is no temperature, and then bloom temperature A minus 1. So in yellow is the raw radiation, if you want, or the temperature. Okay, this is what was done during years and years and years when people don't take into account the non-instantaneous. If you take non-instantaneous rating, is a little bit different. This is Kolb and Ryota, Wimzilla, for instance. This is the first one of the first time where it was made. So in fact, it reached a maximum, temperature reached a maximum, and then decrease with something which is not A minus 1, because you see that the inflaton continue to inject entropy in the bath. So it's not, this is, you don't have entropy anymore when inflaton has decayed. It's exponential decay here, because it is an exponential decay if you suppose the inflaton as a gamma as a constant. So inflaton decay, and when the density of the inflaton in red reach the density of the radiation in yellow, you have the reheating temperature, and then the temperature decrease as A minus 1. So this is, you see, a less steep decrease as from the scale factor of the temperature, because in fact you inject entropy in the bath. So you want to go to A minus 1, but you cannot, because every time you try, you receive energy for the inflaton. So every time you try to go A minus 1, the bath still receive energy and is A minus 3.8, okay? So this is for a quadratic potential, okay? It's important to tell you because it's not the same for quartic potential. I will show you how it can change. If you take a potential which is quartic, the equation of state of the inflaton is not a matter domination anymore. If you have a phi to the 4, you can show that the equation of state, the pressure, in fact, the equation of omega of the equation of states is k minus 2 divided by k plus 2. So it's 1/3 in the case of k equal 4, which means that an inflaton with a quartic potential behaves like a radiation, whereas an inflaton with a quadratic potential behaves like a dust. Okay, so as the inflaton, if for k equal, for instance, 4, the inflaton will be redshifted. So it will, the co-moving, pair co-moving volume, you will lose some energy by the inflaton because it will be redshifted, because it behaves like a radiation. So the injection of entropy is much less in this case, as you can see. This is what the slope for quadratic potential. This is the slope for quartic potential, for instance. Of course, it depends on k, but if you take, for instance, k equal 4, you can see it's A minus 3, 4. And so the A minus, no, 9/5, I forgot for k equal 4 what it is. It is 12, I forgot the numbers, 12, 15, 15 on 8, okay, something like that. But you see that the slope is much more steep and is more like A minus 1, okay. So it was just to tell you that you have an influence of the inflaton potential on the reheating. So the shape of your potential, which is limited by, of course, by Planck value of NS and A star, which is the Planck value on the measurement of the spectrum, give you limit on your potential of the inflaton, and the potential inflaton on his way give you the way of the reheating working. And if you want to refine a little bit more, even a third refinement is to see the phase here where because we have supposed thermal equilibrium where you have not thermal equilibrium. So this is something very interesting too, that what's happening when the inflaton decay? The inflaton decay into two particles, which of course has an energy which is half the mass of the inflaton. This is what you have normally if you suppose now still is just a quadratic potential, which is a dust, okay? I have another inflaton here with decay in another place, if you want, with two photons, which of course has the same energy with them divided by 2. So the spectrum, just at the end of the inflation, it's just made by monochromatic particles, which has m divided by 2. But of course, universe expand. So as universe expand, the wavelengths of the photon, of course, before they collide, the wavelength of the photon will be stretched by the expansion of universe, okay? And when they collide, their energy will be much smaller, and they can begin to reach a thermal bath once it's a long-range direction, of course, because photons are massless. So this cross-section will increase with decreasing energy of the photon. So there will be a temperature, or let's say a scale factor, because I cannot talk about temperature because there is no equilibrium yet. So there will be a scale factor where this interaction between the two photons which has been produced begin to dominate the universe, and the photon go from a monochromatic spectrum to a thermal spectrum. So this is a phase which can take times. And during this phase, I cannot use the classical Fermi-Dirac and Bose-Einstein distribution function. So I reach thermal equilibrium only at this region. Before this region, in fact, my energy of the photon is m divided by 2. I have m divided by 2. I have a region which is quite complex, which is not thermal. And then here I can use my classical equation I know I showed you before, because I know I have a thermal equilibrium. So if I put some physics on that, this is the time increasing from up to down. At the end of inflation, I produce photon with m divided by 2. Then after a little bit after, I will have my photon which has been produced here will be reshifted to a lower energy, whereas I will still produce photon, but much less photon because my inflaton has been diluted. So I produce here, for instance, 2 photons with this energy. A time after, I will produce only 1 photon with this energy because my inflaton has been diluted. So per moving, I will have lost some of them because he has decayed, of course. He has, sorry, diluted, but he has more decayed, so less inflaton is in the universe. And the one which has been produced here, of course, has been redshifted. So the density decrease also. So both density decrease because I have the expansion of the universe, and etc. if I increase the time. I still produce some inflaton too, but the one which has been produced there has been redshifted, and the one who has produced there has been redshifted and diluted at the same time. So you redshift plus you dilute it. So these are two effects you can see here, and you see the spectrum begin to be flat. Okay, from monochromatic spectrum, you begin to reach a flat spectrum, and then the flat spectrum begin to thermalize and to form a thermal spectrum. So this is a numerics results here. So this is the distribution function you got, which is not thermal. So I mean, it's a result we have. So you see that you begin by monochromatic, and then this endpoint here correspond to this point here. Okay. So at T hand, this photon here has been produced just at the end of the inflaton, and this is sometimes after inflation. A little time, this photon here now is there, and this photon here now is there. Okay, you see, you reach a flat spectrum step after step. Okay, and of course, little by little. So from monochromatic, you begin to reach a flat spectrum in blue. So this is the time evolving. And when I reach 10 to my 32nd, my little by little in orange, you see my photon with low energy begin to thermalize and to form, yes, nice, and to form a thermal bath, okay, at a time of 10 to my 30 seconds. So more or less 10 to my 30 seconds after the end of inflation, you begin to form a thermal bath, okay, whereas the end of inflation, I took it to 10 to my 37 seconds. So just to tell you that, of course, and in this case, in red region, you have a classical distribution function of thermal function. So just to tell you, okay, this is, and you have a refinement number 4 if you want. You also have to see the preheating phase, which happen just at the really end of the inflation when you have the first oscillation. So what's happening, in fact, in this case, it is that when you want to produce dark matter, suppose S is my dark matter, for instance, you produce it through what you call a parametric resonance, because when you solve the equation for S, okay, in in the Fourier phase, in the Fourier space. Okay, this is Sk for a given momentum k. This equation, which is just the equation you solve from this Lagrangian, you see it's an equation. If I forgot the expansion of universe here, h is able constant. This is what we call a Matthew equation, which generates a resonance band, okay, or we call it parametric resonance, because it's a system where the number density of S, where so the number density is S square, okay, a classical S square. You see that this factor here is periodic, and it's a system which is very classical in mechanic physics. Here I have a little video. I'm not sure you can see it. So if you make if you have oops, I will cut my sound. You see that if you have a certain oscillation with a certain frequency, the frequency given by S dot and K square, you see that if you impose a frequency on the system here, which is half the frequency of the system, you see, will impose a frequency here. This is what we call resonance. And imposing this frequency, you see the amplitude, in fact, increase and reach a resonance. Okay, so it's called parametric resonance. So for the frequency, which is exactly half of the frequency of the system, so the same, you have a spring here. So this is a classical frequency. You don't have resonance here. Okay, so you see it oscillates at its own frequency. But you see, if I increase by 2 my frequency here, you will see that the system will enter a little, little oscillation at the beginning, will increase and will reach you reach here a resonance, clearly resonance on the amplitude. This is exactly what's happening with the inflaton. So this is the equation of the inflaton. This is resonance. So m phi divided by 2, you understand quite well. Half the frequency is m phi divided by 2, which is the energy, in fact, of the particle in which you decay. So if the energy of the particle you decay is m phi divided by 2, half this frequency here, you will reach a resonance. Okay, but of course, K evolve with a scale factor, so it's a little bit more complex because this function is periodic, but depend on time through K here, which is redshifted. So this is what you observed at the end on the plot. Sorry, I have to go there. Ups. And if you see the evolution here, so this is the value of the coupling. This is the value of K, is K divided by A square, sorry. And so you see that you go from here at the end of inflation, and you will reach every time some zone of resonance. Here you have a resonance, here you have a resonance, here you have a resonance. So when you go in time, so phi decrease, the amplitude of phi decrease, and the momentum decrease, because by redshift, and you see that you will reach some range of resonance. This is solving the Matthew equation. This is what you see here in green. So in red, okay, and orange, it was what I showed you before, classical reheating, and in green and blue, so rho phi is in orange and rho radiation is in red. This was reheating. And if you take a look at the preheating, it is blue and green. You see that the rho phi decrease, in fact, and rho radiation increase, and both reach here kind of equilibrium, it's not equilibrium, kind of equilibrium, and then once it reaches rho phi go to a-4. So you see rho phi is destroyed by this parametric resonance. Every time you pass here, rho phi lose a lot of energy. Okay, just a little things before finishing. It is that we'll need still 5 minutes if you don't mind. But you still have the same reheating temperature in both cases because reheating temperature does not change. So rho phi equal rho reheating at the same time because the reheating temperature is given only by the weight of phi, which is the same phi, which is in both cases. So I will just need 5 minutes more. Sorry, I was a little bit long maybe at the beginning. But adding dark matter is very easy now. It's just 5 minutes sufficient to add the dark matter because adding dark matter is just adding the Boltzmann equation to what I told you before. The only thing is the rate of production depends on temperature, and I have to include here all what I told you before. Okay, the reheating phase, preheating phase, thermalization, etc., is in the rate of production here, production rate. Okay, so and the Hubble constant, of course, Hubble constant depends on rho. So this will act on the rate and on the Hubble constant. All the story I told you will change my Hubble constant and will change my production rate. This is very important because the Hubble constant will depend on a lot. So you solve this equation, and so it's a little bit more complex than the classical Boltzmann equation because the rate depends on your history of universe. You also have to add the inflaton decay because the inflaton can also decay into dark matter. And adding all these systems together, you can compute the radical balance of the dark matter produced at the early universe. The main result we have, so you have the bath who produce dark matter, okay, in this region here. And we showed that around, depending on your cross-section, of course, but around majority of dark matter is produced in this region here, where you have to be careful of all the story I told you before. So if you look at dark matter which are filmed, the main conclusion it is that you have to be careful on your historical on your thermal history of your universe, because it will depend a lot on this region that I just described to you before. So if you take into account preheating or not preheating, thermalization or not thermalization, this is changed a lot. So if you want to see some models where it happens, you have a lot of models where you have to take care of that. High scale SUSY, for instance, you have a cross section which is highly dependent on the energy. So you understand quite well that if your rate depends a lot on temperature, this is where the effect will be stronger, because I told you that you change the temperature dependence. So why in this case? Because you have something which is depending on 1 m Planck to the 4. So you have a rate which is highly temperature dependent. So you have a lot of correction to add. You see is the temperature to the 7 for the radical balance. So result is not so important, but just to tell you that you have a region of parameter space in the red here, which fit with the data. So it's working, let's say, for gravitational mass quite heavy. You can go to 10 to the 8 GeV, for instance, reheating temperature quite okay. But big dependence on reheating temperature. Just to remind you, for classical gravity, no, the dependence is just T reheating. For classical gravity, no, here is T reheating to the 7, okay? And very massive gravity, no. So you also have a radiative decay that you have to take into account. So you see the physics is not finished because you still have loops contribution for the decay of gravity now, so which can also contribute. So a lot of contribution then can happen. Some examples, for instance, you can exchange a massive particle here. You can have a derivative coupling here. You can have two derivative coupling and a massive particle. You have a lot of model where you have to be careful. And you have a Z prime, for instance. You have to be careful of this story of universe. Exchanging a massive spin to a graviton, you have to be careful. Exchanging a dilaton field, you have to be careful. So all these models are models where the effects of the reheating, preheating, termination are fundamental in your computation of the radical balance. Just to tell you that if you look at model where you have higher dimensional operator, be careful, because everything happening after the inflation will change a lot your radical balance computation. And I finish with that. I finish with a very minimalistic scenario we just did with Keith 2 months ago. We just show that because you have so many energy at the end of inflation, you can produce a lot of dark matter. In fact, just to tell you, it's very dangerous because you have so many energy at the end of inflation that you have always to have to be careful that you don't produce dark matter through the inflaton scattering. For instance, just exchanging a graviton, which is the weakest force you can imagine, we showed that you have overabundance of dark matter quite easily for dark matter mass of 10 to the 6 or 10 to the 4, 10 to the 4 GeV. You have overabundance of dark matter for end of inflation energy of 10 to 16 GeV. So you have to be careful because 10 to 16 GeV is not crazy energy at the end of inflaton, at the end of inflation. And this in this region, you have always overdensity. So even with the graviton exchange, you expect to produce dark matter, maybe even above the limit of Planck. So that's my conclusion, that the WIMP first part, I think I convinced you that the WIMP paradigm can be put in questions, but the alternative scenario of the FIMP, for instance, can lead to especially heavy dark matter. In the plot, you see there was very heavy dark matter, but it's not independent initial conditions. So you have always to be careful when looking at this kind of scenario, because you can have a surprise, like we did 2 months ago with the graviton exchange, because you can produce a lot of dark matter because the energy you have at the end of inflation is very huge, and it can compensate any kind of coupling. And it can be observed, of course, by Anita Ice Cube. I didn't discuss about it, but we did some work where heavy dark matter can decay, in fact, if it is unstable, and you can observe EV stuff by that. Thank you very much, and sorry if I was so long.
Okay, thank you for your nice talk. Okay, now it's open for questions and discussion. Do you have any question?
Sorry, can I ask a question?
Yeah.
No,
I forgot. So I forgot you. The work was made. I forgot to put the names. The work was made by Marcos Garcia, Cunio Canita, which is there, Keith Olive, Emilian Dodas, etc. I forgot to give them. Sorry, Cunio. I didn't give any names on the talk, but Cunio is there, and he made a lot of part of this work. If you want to ask him question, he's just next door in Seoul. So technical question he can answer.
Yes, I'm not so familiar with this direction, but the non-trivial time dependence appears because you consider non-instantaneous reheating, right? Then and in the later discussion, I don't see the parameter k, which included in the potential. So you fixed.
Yeah. In the majority of the figure I show you, it was quadratic potential, k equal 2. We did recently with Cunio in December paper where we made generalization with any kind of k. You're right, it's very important because it changed a lot the results. It changed a lot the results.
So it's
the higher you go to k, in fact, the softer is the spectrum. Okay, the spectrum. I mean, if you go to a small k, you have a spectrum. The temperature is quite large, right? But if I increase k, I produce particle already redshifted because inflaton redshift, because k equal 4, the inflaton is itself a radiation. So inflaton, if I have quadratic, inflaton produce m phi by 2, okay? But if I have k equal 4, my m phi, which is effective mass, decrease with time. So the energy produced at the beginning is also smaller, okay? So I have difficulties to read if you want, okay? Instantaneous reheating, you go toward, if you increase k, you go out toward a more and more difficulty to read. So you read much later, okay? Because if I do instantaneous reheating, I say rho phi decay, and all my rho phi go in rho r, easy, all right? 100%, I don't care. But if I have k equal 2, okay, I have the expansion which appear, right? K equal 4, I have the redshift of the inflaton plus the expansion. So I'm less effective, the inflaton is less effective, right? It make time, so it decay much later in time. So which means that the reheating appear later in time, right? Instantaneous reheating is at the end of inflation. Quadratic, it's 10 to the 30 seconds. We did k equal 4. I think everything was 10 to the 10, something like that. I forgot what the value, maybe you can remind, but 10 to the 5, 10 to the 6. So the scale factor for reheating is very late. So the more you increase k, the later will happen the reheating.
Okay, thank you. By the way, in your expression, when we consider linear potential, it looks the temperature doesn't have this dependence of scale factor. Is it correct?
Okay, first you need to define what is the temperature. So you can only define if it is thermalized. Okay, so the temperature, in fact, recently with the paper, it's a good question in the sense I personally used to use temperature before, but I don't use temperature anymore because it's tricky. You have especially the phase where temperature go to the maximum, as you say, it's not linear at the beginning because you go from 0 to max and then to reheating. So at the beginning is not linear. It's quite complex dependence. If you want to make computation, my advice, because we had a problem for the last paper where the referee asked us what's happening before 0 Tmax in this very, very small region. So it took us 2 weeks to solve the problem. Think a scale factor, okay? Temperature, to my mind, temperature is a relic of the WIMP. And we think temperature is nice because we know what is 10 to the 10 GeV. We want to, yes, okay. But if you want to concretely solve, think as a scale factor, not temperature, because you have a lot of cases where temperature has no meaning, okay, or complex meaning. So think as scale factors. That's my point of view. Okay, talking about temperature at the beginning where it's non-linear for me is a little bit misleading, especially because, to my mind, is even not thermalized.
Yeah, the K is the power of the potential, right? Then,
Yeah.
My question is the linear, like the absolute value of the phi, for example.
The shape of the potential, you say?
Yeah.
Yeah, okay, but you can always approximate. I mean, we did any kind of K, so you can develop. Let's suppose you have a potential you can develop on lambda phi power K.
Okay, so we can consider such specific type.
Yeah. We have considered Starobinsky potential in our papers. So.
Okay, thank you.
Yeah, of course. You can have tangent hyperbolic, alpha attractor, okay, and you can always approximate in this development of K. Sorry. Yeah.
Thank you.
So I think that I have a question. You said it is difficult to overproduce dark matter from inflaton scattering, and so in order to get the right abundance, you may have to choose a light dark matter. Maybe,
okay,
and my question is about the large scale structure.
yeah, no, in fact, yeah, it's a good question. I mean, all questions are very good, but I just show you the value. No, it's quite heavy. When I say light, it's not the light. I will just share it just to show you the values because I don't have time. You see, no, don't worry. The mass of dark matter now is 10 to the 6 is a PV. The GV is there. Okay, so I don't have GV. If I go to, end of inflation, maybe 10 to the 18 would be here, okay? So maybe if at the end of inflation, I have M Planck, okay? Maybe you can have problems of this kind, right? Below GV, even not sure. But if you take a gut type end of inflation, PV, okay, PV is okay, okay? You need to be, okay? So this is excluded here, okay? So to exclude the region here, for this mass, you need to go quite large. We still okay. But the surprise, in fact, we did it. I would stop sharing. What was a surprise is that we did, you remember maybe because we did the paper the same day, you mean spin 2 mediator. We did a thermal bath, a graviton dark matter 2 years ago, right? And this was not working. We needed a large temperature because the coupling was too small, and you cannot produce dark matter from a thermal bath gravitationally. Okay, that's what we proved. Or you need a temperature of above the mass of the inflaton, which is possible in some way, but it's complex, right? The idea was, yes, but the thermal bath has less energy than the inflaton itself. So maybe the scattering of the inflaton, okay, by gravity, so inflaton scattering by gravity can produce dark matter because in my bath, I have less energy because my bath is produced by the inflaton, okay? So the inflaton takes time to produce. So the time that the bath is sufficiently energetic, it's already diluted quite largely, right? But at the beginning, inflaton is not diluted. So our idea was simple. Let's try to check if two inflaton collide by gravity. I mean, the sense in the head, right? Maybe the Planck reduction will be surpassed by the energy still have because it's not diluted yet. And it's working, which was a big surprise, in fact. It was a big surprise. It's super simple. And this is unavoidable. I mean, nobody can tell me, I mean, this is minimal model, right? I just have inflaton and graviton. I cannot have less. I even don't have thermal bath. I even don't talk about thermalization. I do nothing. I just have inflaton, graviton, equation.
Graviton, massless graviton. Massless graviton.
Yeah, massless. Yeah, of course, massless.
Our graviton.
Yeah, our graviton, which is a minimal things. And it was working very surprising.
Okay, and do you have a more question?
I had a question about the WIMP direct search. We were discarding the WIMP. you know, you show the excursion regions from the direct detection, and but there's a limitation for the upper bound, heavier region. In that particular figure, they just showed the up to 10 TeV, I think. But in principle, for WIMP, we can go like unitary bounds, say few hundred TeV. But is there any reason that they just cut that scale?
Okay, so yeah, there's some paper, they call it MDM, I don't know, maybe you mean you know it, no, HADM, very heavy dark matter. So there is a study, okay, so they made derivation of dark matter of PeV, even EeV, 10 to the 9 GeV, okay? So you can go, it's possible. In this case, you need a cross-section of around 10 to minus 22 sigma V, I think, or 10 to, it's 10 to, from 10 to minus 26 to 10 to minus 22 for cross-section. There is some study for that. Okay, you can go there.
Is it just a simple separation, or so without losing any sensitivity in the experiment?
No, you can. I think you can go to the analysis. They made analysis with the data of Xenon. I think they went 10 to the 8 GeV. I think they went there. The only problem is here. You need the coupling super large.
Oh, sure.
So to have the good recarbonance, because of course the problem you have few particles. Okay, you have much less particles because it's heavy, right? So to see something, you have to compensate with a large coupling, which is above unitarity. Okay, so you need to have a model which is a little bit strange, because I'm even wondering, this is a question I had, maybe there is dark matter annihilates in the early universe with such a large coupling. I mean, the coupling they need is very large. But yeah, it's, I think 4 weeks ago, I read the paper where they made the study. It's a group, always the same group. They don't have models.
I see. So nevertheless, the dark matter model just below unitarity bound will be still viable.
Yeah, the idea is unitary bond, you know, is coming from the fact it's thermal, right? Unitary bond is thermal. Thermal, you have the limit of unitarity. Now they say, suppose it's not thermal. Okay. And they go and they just make with the data. It's exactly the same plot you see here. They just go to but in fact, no, what they use, I'll tell you what they use. They use multi-scattering because there is less dark matter, but the coupling being so large, then one dark matter can do multiple scattering, and this is a signature.
Oh.
Because they can scatter three, it's the same kind of plot you see here, but they suppose 1 scattered, 10 scattered, 100 scattered. And if you increase the number of scattered, you have a signature which makes something visible. So they compensate the few number of events by the number of scattering because your coupling is large.
I see.
So it's and the signature is a little bit different because you have S1 and S2, and you can correlate S1 and S2 to see it's the same particle which has scattered several times. That's the way they do.
I see. Just out of curiosity, what about the neutrino floor in that region? Is it still there? Neutrino floors. The background
is very low. At this energy is very low because.
But I think around that region, the main is coming from the astrophysical extragalactic, I guess.
Well, for very heavy, massive dark matter.
Yeah, it could be at some point there should not be neutrino background. I don't know. It's just out of my curiosity, but
you know, I don't think it cannot. I don't think it can. I don't know about neutral. I don't. They don't. For sure, they don't make it. For sure. Oh, yeah. You can if you want, you can, but there is no paper on that. Okay. I was trying to find a UV model or correspond to what they proposed, but I didn't find it. It's very hard to have this kind of model.
Oh yeah. All right. Yep. Thank you.
I have 2 questions. You mentioned about preheating, importance of the preheating for dark matter production, but you also mentioned the reheating temperature can be still determined by the perturbative
Yeah.
reheating. So
very important
that might
point.
be a
Thank you.
loophole to that discussion. And also another question is about the effect of the preheating for gravitino production. Recently, you also wrote a paper on slow gravitino, so you might have a larger production also gravitinos from preheating. So can you make a comment on that? Two aspects on the preheating.
So for slow gravity, no, I mean, we can discuss together. No, it's a complex story for slow gravity. No, so the Kolb make a paper with a mistake, okay, and so we just underline the mistake, and the referee accepted our paper directly because we underline that the paper of Kolb is wrong, because you have to mix gravitino and inflatino, and the fact that when you use preheating means inflaton, right? Inflaton means inflatino. Inflatino means mixing with gravitino, because gravitino is a mix between inflatino and gravitino, longitudinal mode of the gravitino. And so you have to diagonalize the matrix, and is much more complex than one Kolb using the. So just for the paper of Kolb, that's the mistake of Kolb. And so you don't have slow gravitino, or you have slow gravitino sometimes, but it's not dangerous because you have to diagonalize the matrix. So except for this gravitino, the question you ask for the preheating, I think is a key question. I think Kunio will agree with me, because we work on that now. We begin to work on the literature of preheating. We are not sure that, I mean, we're not sure that every people who do preheating really understand preheating. We don't understand preheating. I think it's quite complex. You cannot, I think Kunio will agree with me, but we discuss a lot. You cannot reheat with preheating. I think that's a point which is not said in literature, or is sometimes little sentence. You say you need a decay at the end. You know, you need to have a perturbative something, a scattering or a decay, whatever. So preheating is non-perturbative, but you need something perturbative at the end to transfer the energy of your inflaton in the bath, scattering or decay. Preheating is only useful if you want to produce something like a dark matter, if you want to make biogenesis, if you want to have a phase which is matter dominated to slow down the expansion of the universe, if you want to produce right under neutrino, leptobiogenesis, whatever. In this case, yes, preheating is important because you will produce a huge amount. In the rest, the plot I showed you here, which is very important, I think, it's my student who made this plot, and we were all surprised. Well, not surprised, but I will show you again. If you see this plot here, okay, it's that's important. I don't know if I can make a zoom. Yes, you see, the green is what you produce by this resonance. You see, it's a resonance. Okay, it's using lattice easy. Okay, it's a code because you need to put lattice. I mean, to compute the solution, you don't have an analytical solution of that, right? It's a code. You use code for that. You see that you reach this region here where the density of the inflaton in blue and the density of radiation in green is the same, okay? Because inflaton, you lose inflaton, you go from orange to blue, and of course you produce a lot of radiation. But after a while, what's happening? You have back reaction here, in the sense that you produce radiation, suppose the radiation is Higgs, right? Suppose it's Higgs. You produce Higgs and the Higgs produce inflaton here, right? It's not a thermal equilibrium, it's a kind of. But after a while, here, you will not reach any band, you see? You will not have the resonance, parametric resonance, right? The equilibrium is valid, not because it's a thermal equilibrium, not because the coupling is large. In fact, the equilibrium between the two is there because you have resonances, which happens. So you have still a lot of resonances here, right? But there will be a moment where the K will be redshifted here, right? And the K being redshifted, you will reach a region where you will not have any band to pass through, right? So the inflaton will not be able anymore to produce radiation by this burst of resonance. And so the radiation will go to A-4 and will leave the inflaton. So the only effect of parametric resonance is twice. There is two effects. First, you will lose energy compared to no parametric resonance in the inflaton, because inflaton we have lost energy in the burst, okay? In this region here, inflaton will have lost energy. And Second things, if you produce something which is stable, okay, like the dark matter, or something which is long-lived, and we have an effect. Suppose you produce something which is long-lived, right, in green, not radiation, right? M-3, a massive dust. And the dust decay, it will have some effects. Suppose you produce a particle which used for biogenesis, and you make the biogenesis here, it's okay. But for the reheating is useless, because once the inflaton will not have any resonance band, okay, because this will disappear, the story is the same. From here, it's exactly at the end of inflaton. The only thing it is that you have the same story, except that rho end is not the same. You see what I mean? You have the same story that without preheating. So that's why in red and orange, which mean perturbative, and green and blue here, which is non-perturbative, you have the same reheating temperature because it does not depend on your initial condition. What changes when it happens? Of course, it happened earlier in the case of preheating because you have destroyed inflaton. So of course, the reheating happened earlier because you have less inflaton at the beginning in a sense, right? It's the same that changing rho NF inflation. So it happened before. But the condition of having both the same is the same. The rho reheating will be the same, which is the width of gamma phi. So which means the reheating temperature is given by the perturbative physics. The time when it happens is given by the non-perturbative physics. So the preheating will act on when it happens, and the perturbative will act on the value of it. Okay. This is, I think, very important, and not, I mean, we are working on that, so I hope the paper will be released maybe next month, but it's something I think important we have to underline in the literature of people, because people talking about preheating, sometimes they believe they can reheat with preheating. It's not possible to reheat with preheating here, because this equilibrium, if you want, happens only because you pass through resonance band, which disappear with time.
Okay. Yeah.
Very good questions, huh?
Okay. So are there questions also?
Sorry, one more.
Yeah, pleasure.
I didn't understand correctly, but in the later talk, you discussed basically you solved the Boltzmann equation for the dark matter and radiation and the inflaton, and I don't remember correctly, but the result seems to highly depend on the spin of the dark matter. No?
Oh, yeah.
So you showed the scalar case and the fermion case. But
So very good question. You ask all the very good question. I will choose just for the graviton, for instance, because it's easiest. For the graviton, it's very obvious. The spin effect of the spin, because if you have a scalar dark matter, by conformal invariance, scalar dark matter and fermion dark matter, you see. So scalar dark matter, you don't depend on the mass of the dark matter in this case, because you have conformal invariance in sense, okay? Which means, I mean, you know better than me about that. But the energy, because if you change a graviton, in fact, you are coupled with the energy momentum tensor, right? And the energy momentum tensor is highly spin dependent, right? So energy momentum tensor for a fermion is proportional to the mass of the fermion, right? So you will have a rate which is proportional to the mass of the fermion. Okay, that's why in red is a fermion here. You see difference, blue is scalar, red is fermion. So it's very different. But for a scalar, you don't depend on the mass of scalar. This is kinetic factor. You don't care about this. This is kinetic factor. Who cares? This is important factor. You see, you don't have mass of dark matter appearing here, right? Because it depends on the potential of V of S, if you want. Okay, so the mass is a kinetic term we depend for the scalar. It's d mu phi, if you want. This is d mu s for a scalar, right? Whereas is psi bar gamma mu d mu psi for a fermion. So it's proportional to the mass of the fermion for the fermion, and it's proportional to the energy for the boson. Okay? Wow. That's why you have here, you see, these two difference is m phi to the square. You understand quite well. The difference between these two formula is m phi squared divided by m chi squared. In fact, is the m phi squared is the energy, right? d mu s divided by m chi square, which is psi bar gamma mu d mu psi. It's t mu nu s on t mu nu psi. That's the difference between the two.
I see.
Right? Because on shell, you produce on shell, right? On shell is proportional to the mass of the fermion, right? But to the momentum square of the boson. Okay? So if I have a massless boson, I still produce it. If I have a massless fermion, I don't produce it. Gravity is not fair with fermion. Okay? So that's important point. Okay? You can produce by gravity scalar, massless scalar. You cannot produce by gravity massless fermion.
Oh, I see. Okay.
That's a very interesting point. And for the Bernal et al., there was a paper of Bernal et al. Just after us. They redid the same computation than us, adding self-interacting dark matter, Bernal, and I forgot Bernal, you will find. And they did the vectorial. Vectorial is the same as the boson, okay?
Vector.
Yeah, vector is a boson. It's 3 boson if you want. So you have d mu, a vector, you have a phase which is d mu something, right? So
I see.
it's the same than the
Okay.
But it's interesting, yeah. And this was also a very interesting result that the gravity. So you have some conformal. I mean, we discussed about it with Cuneo several times. You have some conformal invariants who can justify just quickly why you have this dependence. But I explain you through the coupling that you see that that the scalar is very different from the fermion.
Interesting. Yeah. Thank you.
Yeah, it's very strange. It's very strange because you will think naturally, oh, it's gravity, so gravity should not care, right? No, gravity care because the spinor, it's coming from the general relativity, okay? Because okay, it's easy to understand why it's coming from, because you have gamma mu, and gamma, if you change general relativity, will change the metric, right? The geometry. If I change my metric, I will change my gamma mu, okay? Because my gamma mu depend on my metric. So general relativity acts on the fermion much more than it acts on the scalar. Scalar is d mu, okay? But gamma mu would change. So this is a spin connection, right? So general relativity acts more on fermion through the gamma mu, if you want, than on the scalar. Because the gamma mu will extract me the mass. Gamma mu d mu psi is m psi by Dirac equation. So gamma mu d mu is a mass, right? d mu phi is not a mass.
Okay.
So there is some subtlety there, but it's interesting. So the conclusion is very good. General relativity does not treat the same way fermion and boson. We know it, of course, when you compute mu nu, but there is some important consequences on that.
Okay. So
I just wanted to make sure one thing. I guess you are assuming the scalar, in the scalar dark matter case, you are assuming scalar dark matter minimally couples with gravity.
Yeah.
Right? Yeah. So if you include non-minimal coupling, then a coupling will be different, and
of course
prediction will be changing.
Right? Of course. You can kind of conformal dark matter, right?
Yeah.
Yeah. You can use the coupling and change the coupling, having a B-metric theory, for instance. This can change, of course.
So I have a question on the maximum temperature during reheating. And I think you said if you take the K different from 2, let's say K equal to 4, you don't have you can define the effective mass for the inflaton, and you have reheating ends. I mean, the reheating is delayed if you have field dependent inflaton mass, and but also you have to change the equation of state from 0 to 1/3 in your calculation. And so I think that the UV freezing depends on the ratio of the maximum temperature to the reheating temperature, right? And then I'm asking, of course, if you know the interaction between, let's say, dark matter and the thermal bath, you can easily calculate in terms of the ratio of the temperatures. but the temperature ratio also depends on the equation of state and the form of the inflaton potential during reheating. So, is there any, study just you can just increase the ratio as you increase K value, or is there any analytic expression?
Yeah, the ratio increase, and of course, your dark matter. I'm just looking now in live our papers, because this is a paper we did with Cuneo in December, just to check I don't say silly things. I'm watching in live.
Also, I noticed that you also mentioned the Bernard's new paper. Also, he took the ratio to be, let's say, from 1 to 10 to the 3.
Yeah.
10 to the 3 at maximum, and then, but he didn't mention, well, he mentioned.
Yeah,
but
so I have numbers here if you want. I can give you numbers because we did it. I will share my screen. This is a paper we did with Cuneo and Keith and etc. You see, so this is temperature as function of A on AN, you see. So this is, I think, quadratic inflaton potential. I forgot if I have the quartic. Quartic here, you see. So you see, so AN go to 10 to the 7, around that, right?
Yes.
And you have a reheating temperature of 10 to the 9 and a maximum of 10 to the 13, right? Some examples.
Okay, so that's 10 to the 4th in that case.
Yes, and it's true that this, okay, after we can change it a bit. So K equal 4, okay. And you have effect of the effective mass also. I don't want to go into details, but when you have lambda after 5 to 4, you have an effective mass. You generate effective mass also to the decay product. So you have to be careful also. So you have subtleties that I didn't go into account, but you have a lot of other effects because you see if you have a coupling lambda phi square s square, you will generate a mass also to s square, which can, the cross section depends on the mass.
Inflaton quanta.
Yes, exactly.
From the inflaton condensate.
Yeah, lambda phi to the 4, the mass change. So you have an effective mass for phi, which change also, and an effective mass of the final product also. So there is some sensitivity, but you see it's around 10 to the 9, 10 to the 8. Yeah.
Okay.
Very good questions.
Okay, I think that we have a pretty good question, but without questions from the students. So I asked them to prepare some questions, but maybe just among us, we have already good questions, discussions.
It's so nice to give seminars in Japan or Korea, because we always have very good questions when we give seminar here.
Yeah,
it's very great.
Shuntaro Aoki is the new postdoc in our group. So,
Sorry?
You can say hello to.
I'm Shuntaro Aoki from Japan. Yeah, I came CAU from this April. So I'm now a new member. So nice to meet you. Yeah.
Very good. As a postdoc or student?
Yeah, postdoc. Yeah.
Postdoc? Okay, good. You work with Yunmin?
Yeah, in inflation in the context of supergravity.
God. Yunmin is following what I'm doing, because when I knew Yunmin, he was not doing that at all. No, he was doing formal stuff at DESY.
I'm following you.
Yeah,
I'm paying attention to you. So
yeah. I do dark matter, I go to inflation,
I'm going to check some errors in your calculations.
You did one mistake. I remember.
It was my single authored paper, so there was nobody.
Yeah. I noticed it.
Okay, so we have a good discussion. So yeah, I think that we can discuss in a real workshop next time.
Yeah. And Cuneo is there. I mean, Cuneo knows all that. So if you want some technical details, I think it's an interesting subject, by the way, for anyone working there. It's I don't say it's vierge. I mean, there are things to do, but when you dig, a lot of things is not so well done. I would say, and I think is even not so well understood. I think.
Okay. Yeah. Also, we'll have further discussion with Kunio when because he is in Korea.
Yeah.
And okay. So
Very
then,
good.
are there urgent questions? This is the last chance for your questions.
If not, you can come to Paris to ask me questions.
Because we need to go to Paris to ask the questions. If you don't ask a question now, do you want to go to Paris? Okay. Okay, then let's thank the speaker again, Yann Mambrini. Thank you for your time.
Thank you.
Yeah, see you next time.
I thank you. Always a pleasure, I told you, to give a seminar in Japan or Korea, Asiatic country.
Okay, thank you.
Very good.
Okay.
You're great.
Okay.
See you.
Okay.
See you.
Send me your top 5.
Yeah, I will.
Okay, thank you.